So at this point, what I want to talk about is an application of 2D motion, or multidimensional motion, really. We're calling it projectile motion. This is also known, to some people as ballistics or ballistic motion. So we're used to thinking of ballistics as being like, police detective stories, the police shows, how they analyze guns, and they fight to figure out whose gun shot the person who's dead. But ballistics really just means anything in ballistic flight, and ballistic flight basically means you're subject only to gravity. That's the only acceleration. So projectile motion, the condition that has to be satisfied in order to have projectile motion or ballistic motion is that the magnitude of the acceleration vector has to equal g, and it has to be constant. And all that really means is that you have a gravity field that's accelerating everything towards it, or everything downwards, at some specified rate g. G on Earth. On Earth, g can equal 9.8 meters per second squared, or it can equal 32.2 feet per second squared if you use the imperial system. But for a lot of places, we just like to leave it as g, and that makes a lot of things easier to manipulate. I'm going to focus a lot on symbolic math and trying to show you guys how to do things symbolically and only really substitute in numbers at the end. Because I think it's important to learn how to do that. It makes things easier in the long run, and it develops a higher level of thinking. So, what exactly does this a vector equal? And you can think of this as also as acceleration due to gravity. So maybe we could say for projectile problems or ballistic problems, acceleration is just the acceleration due to gravity, and what does it equal? So here are some possibilities. Say you've got it really all depends on your coordinate system, but say you're standing on the ground here. So there's our ground, and that's my line that's supposed to be the ground, but didn't quite come out. And oops, pick a color. No. All right. So let's start here. There we go. There's our line. Okay. And we've got a person, say, standing here, whatever, I don't know, throwing a ball, something like that. We want to define a coordinate system for this problem. So what we're going to do is we're going to put our y going vertically, and our x is going horizontally along the ground. So what is g? What is our acceleration due to gravity here? Well, here's where it's pointing. It just points straight down. And if we try to express this in our coordinate frame, the easiest way to do it is use I and j components. So you'll recall y is positive, and that means that j hat is a unit vector going in the positive y direction, and then I hat is a unit vector going in the positive x direction. So for this case, gravity is going in the y direction, so we know it's going to be g times j hat, and then the last question is, what's the sign on it? Well, it's going down, and we have our y arrow pointing up, so the positive y-axis goes up, and acceleration of gravity goes down, so ag is negative g times j hat. Now, so let's call that, example 1. Okay. Now, for example 2, let's do that. Let's say we've got, say, a building. Okay, so there's our building, and here's a person standing on the building, and the person throws a ball down like that. Now, for some reason, we decide that it's more convenient in this problem to have y going downward, and then x going outward from the edge of the building. So that x is always, how far this projectile has gotten from the... Ooh, that's neat. Never seen that before. So if I do that, somehow I get a little circle. Anyway, so this projectile here, goes x away from the building while it goes y downward. So, we decided we like this for whatever reason. So in this case, gravity here's our acceleration due to gravity is like that. And in this case, acceleration due to gravity is still in the y direction, right? So it's still g times j hat, but now gravity is pointing down and y is pointing down too, and gravity is pointing down. So acceleration due to gravity is positive g j hat. That's example 2. Example 3 is even wackier. So let's say we have an object starting from this point here, and we define coordinate axes. This object is moving in 3 dimensions. So we do say, we're going to say, come on, draw. There we go. All right. So we're going to say this is our x coordinate, this is our y coordinate, and this is z. And we're going to say gravity is going downward. A sub g, doink. So imagine, this is like x and y are sort of define a plane that's the ground. So this is the ground here. There's stuff on the ground. It's like that. Maybe this coordinate axis, this origin is like a corner of a room or something, and then an object gets thrown into the room somehow. So imagine this arrow is sort of coming into the room, so it's like coming out this way. You get the idea. And you want to talk about the motion of this object. Well, what's your gravity here? Well, it's not in the y direction like it was before. It's not in the x direction. It's actually in the z direction. So a sub g here, I don't have room over there, so let's do a sub g here is going to be g times k hat, and then it's pointing downward, and positive z is pointing up, so it's negative g times k hat. So the point here is that it can be all kinds of different things depending on the problem setup and the axes you use, your acceleration of gravity. So all we know for sure about magnitude of acceleration of gravity, or about acceleration of gravity, is this magnitude equals g, and direction of the acceleration due to gravity depends on the situation. Okay, there's my chicken scratch. So I'm going to show one more example in the next one, and then we'll pause and I don't know, something.